Okay, so let's start. So just a reminder, this is the next to last lecture. I'm sure we are all excited. My plan is to try to finish everything I wanted to talk about today and then spend most of next time reminding you what we talked about and potentially answering, reviewing and potentially answering questions. So let's see how this goes. One point that I want to make with respect to what I'm saying today and mostly today, I'm going to, as you've seen at the end of last time, I'm waving my hands a lot in the last lecture and this one. So the topic of clustering and the topic of dimensionality reduction that I want to get to later today, both of these are very technical. And many of the algorithms are difficult to implement for various reasons, involve a lot of linear algebra. So I'm not expecting you to know all the technical details. In some cases, I'm going to give you kind of just a glance of them to understand what's happening. And for those of you that are fluent in linear algebra, it might give something. I'm going to skip a lot of technical details. My real goal is for you to understand the key ideas, difficulties, challenges. Eventually, you're going to, unless you want to work in this area, you will probably use software packages anyhow. So hopefully this will give you an understanding of what you see and how you can play with them. You probably saw some of it already in the problem set, the last homework that we've given. You're playing with two different algorithms. We don't ask you to implement anything, but rather use data, play with it, develop some understanding for what's happening. And that's the level I'm going to teach. But please ask questions. Yeah.
I was wondering for the final exam, to what extent would we need to understand? We have to implement these?
So I'm going to get to Kmeans in a few minutes again. Kmeans is the only algorithm that is easy to implement and you can do yourself. You don't need to do anything. It's really a few lines of code. I do want you to understand Kmeans. And also notice that Kmeans is an EM algorithm. So we talked about it also as part of EM. I'm going to make sure that you understand this. So Kmeans is the clustering algorithm that you definitely should understand what it does. And that's why this is the center of the homework also. Other questions? So this is where we started last time, and my goal was to convey the idea that clustering is, one, not really a learning problem, two, ill-defined, difficult to understand what one wants, and difficult to evaluate. And that's something that is not because you're taking a class in it, is because that's the nature of the problem, and everyone who's trying to do clustering suffers from the same kind of issue. So once we talked about this and we ran over a lot of examples and some of the key ingredients of clustering, we got to a couple of definitions that are important. So on our way to trying to define quality, we define these two notions. One of them is what I call a cluster scatter, which is the average distance to a representative. So we're giving m points. We denote, we assume that we have k clusters. Capital C, J, is the cluster. And I'm assuming also that each cluster has a representative Zj. At this point, I'm also assuming that Zj is a member of my set of points, but we discussed this and saw that sometimes it's not necessary. Given this, we can define this dj, which is, a quantity that we want to minimize because it measures the average distance from a point in a cluster to the cluster representatives. As a function of that, we also define a global quantity, the global clustering scatter, which is the average over all data points, over all m data points of the minimum distance from the data point to its representative. Now, I also mentioned that this is really, even though we call it the quality of the clustering, really it focuses on the within perspective, sort of within each cluster. You could imagine also thinking about some other metrics that measure distances between clusters. And we're going to get to this a little bit later today. But given that we have these two qualities, which I'm writing here again, we could also think about what would happen in the case of the optimal clustering. And the reason I wanted to reason about this is because thinking about it allows us to see that this global quality, in the case of optimal clustering, is basically a weighted sum of these local scatter measures of each cluster, the DJs. The reason this is important because this is really what drives, or this is one way to think about what drives K-means, the algorithm K-means. So what is K-means? It's an algorithm that iteratively splits the data points into K clusters. K is given. Every round, once it splits into K cluster, it chooses a representative within this cluster. And then using these representatives, it splits again and keeps on going. So how exactly do we do it? We initialize, step one, we initialize the centers randomly. This is something that you can play with in your homework to see what happens with different initialization, but we initialize it randomly, so K centers. We cluster the points. How do we cluster the points? Each point chooses its closest representative, and that's how we have this joint clustering. Now that we have clusters, each cluster chooses a new representative, and the way we do this is step 3, is we choose a representative that minimizes the DJ for each one of the clusters separately. When we looked at the definition of this DJ, we noticed that this is really a search problem in principle. Try all examples in the cluster and see which one of them minimizes it. In some problems where you don't care that the representative is a point in the data set, you can do it in a simple way. But in principle, what we want to get in step 3 is a representative that minimizes this DJ scatter measure. Once we have this, we can compute capital D and see if we are happy. We use D as the quality of the clustering. If we are happy, we stop. If we are not happy, we go back to step 2 and cluster again using the new set of representatives that we got in 3. How do we decide whether we are happy or not? There are multiple ways of doing it. What I'm suggesting here is relative improvements in the measure D. When you run it, you will notice, in the homework, you'll notice that sklearn actually does it for you. They decide on everything, although you can play with it if you choose to. So they decide when to stop, and you can decide whether you like it or not. That's K-means. Questions? Yeah.
On the homework assignment, when we use sklearn for K-means, do we need to randomize our data first?
So let's think about it. Does it depend on the ordering? Yes, so I have the data ordered at x1 to xm. So So if I permute the data, it doesn't matter, right? In this algorithm, it doesn't matter. So what we ask you in the homework is to use Kmeans and also to use, which I called hard EM, or sometimes called in the literature truncated EM, and also to use true EM, which is GMM in the problem set. And the only difference is that we, in the intermediate step, where we cluster X1 up to XM into their clusters, into their centers, if you want. Here we do it in a hard way. Each point chooses a center and sits in its cluster. In GMM or in EM in general, each point, a fraction of each point goes to each cluster. That's the only thing. So it's going to be a little bit more expensive computationally because you really maintain a probability distribution on where am I over all the K clusters. At the end, you're going to truncate, right? So at the end, you're going to make a decision in the final step for each point where it belongs to. Just because we ask you to make decisions, in principle, you could maintain probability distribution also at the end if your goal is to use this perhaps as input to another algorithm. But if what you want is to make a decision, you're going to truncate and choose the highest probability as your cluster. Questions? Okay, so that, as I said, this is really the key algorithm, and there are many things to say about it. I later talked a little bit about the existence of some other generative models. I'm going to skip that. I want to stop for a second on this example because, again, this is an important example for you to internalize. It basically says there's no truth in clustering. There is interaction between the metric that you choose and the algorithm that you choose. Two different algorithms with the same metric will give you different results. The same algorithm with two different metrics will give you different results. So if you look at example 1 and 2 here, it will show you same metric, different algorithms. If you look in 2 and 3, it will give you an example of same algorithm, two different metrics, and you get different results. So that's, again, an important thing to understand about clustering. And I'm going to get to it a little bit at the end. So the next thing I wanted to talk about, and I started last time, is what kind of inputs can you expect in clustering? What we had in mind before is that we have a set of points and we have a metric. And therefore, we can compute the distance between any 2 points in our data set. Right? That's what we need in Kmeans. We need the ability to compute distance between any 2 points. In general, this may not be the case. It could not be the case for many reasons, either because no one gives you a distance metric, people just give you distances between some of the points. It could be because you have way too many points and you cannot afford computing the distances between all of them, and could be other reasons. So some other scenarios include a set of points, a subset of the pairs have distances between them, and even, and I'm not going to talk about this set of algorithms, but it's good to know that they exist, even what is called constraint clustering, where the input is not necessarily coming in terms of distances, but in terms of constraints on these 2 points have to be in the same cluster, these 2 points can never be in the same cluster, and there could also be a combination, some distances and some constraints. Typically, when we have this kind of input, the method that we're using are graph theoretic methods. So we think about all the points as nodes in a graph. We think about the distances or similarities. Choose your favorite as edges. If you can compute all the distances, then you have a click, a complete graph. In general, you will not have a complete graph. This will be your input. And then your goal is going to be to decompose this graph into connected components. Sort of eliminate some of the edges, keep connected components, and think about each connected component in the graph as a cluster. Again, there are many, many ways to do it. And some of them could be, you can think about as very, very simple algorithms using maximum spanning tree. We talked about this algorithm in a completely different context of learning probabilistic trees. But basically, the idea is you have a graph, and you want to be able to eliminate a lot of edges based on the similarity function. So I'm not going to dwell on this algorithm because it's not so important. The important thing to think about is that all these algorithms that you were thinking about as, here's a graph, I'm going to eliminate some edges based on one criteria or another, they are all local algorithms. When you decide whether to eliminate an edge or keep an edge, you look at the two nodes this edge sits on, and you make a decision. And these local algorithms suffer from a lot of problems. All the examples that I've shown last time, and I'm going to show a few others, of two circles that are embedded, nested in each other, or these X's, or any other combination, all these will suffer from local methods, right? Because you really have to step back and see what is the structure of the data in order to decide that these two nested circles really, you have to disregard local distances and look at something else here. So I'm skipping some of the slides here that talk about local graph theoretic methods, and I want to talk about something that is motivated more by this. And these are global algorithms. So if we want to think about global algorithm, the question is, how do we want to partition a graph into natural disjoint sets when we think about things globally? So let's think about these two, or this set of points, or I'm scaling this up here. And I think it's clear how you want to split this, right? You want to think about lines, two lines. Nevertheless, as I said, local approaches will not do it. So how can we partition a graph into natural sets? Okay, so one way to think about it, and again, I'm assuming that all of you have seen these notions before. If not, you see it here. These are very simple notions. One way to think about it is using a notion of a cut in a graph. So if you have two sets, A and B, each one of them is a set of points, set of vertices in the graphs, I can think about the cut between A and B basically as the sum of all the weighted edges between A and B. So I'm looking at U in A, V in B, W, UV is the edge between U and V, and I'm summing this. This is the value of the cut between these. So one way to think about partitioning a graph to two sets is to think about minimizing this cut value. Make sense? And we know that there are efficient algorithms to compute minimal cut. So that's what I'm going to start doing. Now, this is a binary split of the graph. I'm splitting the graph into two pieces. If you want to split it into k pieces, you're going to do this recursively. You're going to take each piece and keep on splitting it. I'm sure that you can come up with examples when this is not ideal, but that's what people typically do with these kind of algorithms. Okay, so now that we have this notion of a cut, we can think a little bit more carefully. Here is, again, a data set. and I want to use cut, what will happen? Any guess? What will the cut do here? Yeah. Where do you think the line will be drawn between? Say again? No, so A and B, I'm going to deal with all the points that are on the board. So I'm going to find A and B, such that the union of A and B is everything that you see here. And I'm asking what will be A and what will be B. Okay, so cut of AB means that I'm going to search over all possible subsets A and B of this, such that A union B is everything, such that the cut is minimized. Yes?
It's going to be everything on the left is A and the right is B.
So you think that the line is going to be here. Can you see this? Or you hope that the line is going to be here. And I think all of us hope that this will happen, but it's not going to happen. What will happen is this. And the reason is, if you think about it, is that cut would prefer not to touch too many nodes. And if you put everything in the middle, the number of edges between sets A and B is going to be large. If you cut one point, the number of edges is linear, right? If you cut it in the middle, it's quadratic. Maybe it's n over 2 square, but it's still quadratic. So cut, even though it seems very intuitive, isn't going to do it here. So what should we do? And this will be the second cut if you want to do it again. So the cut values depend on the number of vertices or the number of edges between A and B, and therefore they're going to look for the simple solution, easy life, and not do what you want to do. So to fix this, what we're going to do is we're going to normalize. So what we're going to do is we're going to find a way to normalize the size of A and B so that we force the cut to do the right thing and not kind of escape into an easy solution. The way we're going to normalize is with measure that I'm calling here association, ASSO, between A and V. V is the set of all vertices. A is a set, is a subset. And the association between A and V is the sum over all edges from A to the rest, from A to V of WUV. So this is really the total connection from the nodes in A to the graph, or the rest of the graph. Now I can normalize. So I'm going to define, rather than cut between A and B, a normalized cut between A and B. It will be the cut between A and B divided by the association of A and the rest, plus the cut between A and B, normalized by the association between B and V. This way, in fact, what you get is what you want. It really splits around the middle and takes all these group of nodes that are close together, puts them in A, another set of points that is pretty much close together, puts it in B, and we get what we want. Now, if you think about it, you can also define association within clusters. So what I did before with the normalization, I define it between A and the rest. I can also do it within. So what I'm going to do is I'm going to call association A, comma A, be the total weight of edges within A. Same thing, association BB. So what I can define now is above I had the normal cut, which has something to do with two sets. And now I'm going to define the association between A and B, and I'm going to define it again, the association within A, normalized, here at the bottom left, and the association within B, also normalized to the size of B. What is interesting about this? Let's see. So now we have two measures. One of them is a dissociation measure, which we want to minimize. Very similar to the stuff that we talked about before. But we also have a measure of association within clusters that we want to maximize. So this is the same conflict that we had before when we talked about Kmeans, or even before that there are really two things that you want to do. You want to, in this case, we're talking similarities, so I want to maximize the similarity within clusters and minimize the similarity across clusters. Or if you want to talk about distances, I want to maximize the distance between clusters and minimize the distance within clusters. So before we also said that this is how to do. And therefore in K-means we really don't think about the across cluster so much. We just think about within clusters. What happens here? So let's do a little bit of algebra. So I'm going to start with this normalized cut measure that I want to minimize. It's defined as the cut of AB normalized plus the cut of AB normalized relative to B. I can write this as B is just A union B. So this can be written as association between A and B minus the internal association of A, normalized to the size of A, the same thing for B. A little bit of algebra. This is 1 here, this is 1. So I have 2 minus the internal association of A normalized plus the internal association of B normalized, which is 2 minus the normalized association as I defined it before. So what did we get? We got a nice relation between the normalized cut, which I want to minimize, and the normalized association, which I want to maximize. And they actually agree with each other because there's a negative sign here. So basically, for the first time in clustering, if you want, in the history of clustering, what we have is a way to relate what we want to minimize and what we want to maximize and optimize them together. So this is the nice thing that we get here with this normalized cut algorithm. So basically, the two partition criteria that we discussed before, minimizing dissociation measure and maximizing the within association measure, are related, and therefore we can satisfy them simultaneously. So that's a success. Now, the downside of this is that unlike cut, that is easy to compute, normalized cut is hard to compute. It's an NP-hard problem. The approximation algorithm for it are based on spectral methods, eigenvalue methods. I'm not going to talk about. I'm going to mention eigenvalue problems again in the next few minutes, but basically you can use a subroutine and use it. So for some time, spectral methods were very, very hot in clustering in general or machine learning in general. I think now they're less hot than before. In practice, sometimes they work better. Most often what I found is that K-means actually works extremely well, but it could depend also on applications. Anyhow, this is a good set of algorithms to know about. Okay, to summarize, we talked about the nature of clustering. We talked about various algorithms, and we also talked about this problem. And I want to finish this with just throwing a very quick hint that because of this picture, because you show that there is dependence between the metric and the algorithm, a very natural thought is to say, I'm going to learn the metric rather than give me a distance metric or a similarity metric that is natural in your domain, and then choose an algorithm and run, can I learn the best metric for my clustering algorithm? So fix a clustering algorithm, learn the best metric for it. In order to do it, of course, you need some supervised data, some annotated data, which you don't always have. I mean, we started clustering with the problem that here is data. How do you understand its structure? No label data. But if you do have labeled data, then you can do it. So the standard way we think about clustering is from left at the bottom, you have some unlabeled data. You choose a distance metric. I'm going in a circle like this, clockwise. You choose a distance metric. You choose a clustering algorithm. You partition the data. So, and that's okay. But you could also think about extending this unsupervised, no learning paradigm, where you place everything inside a learning algorithm. So I'll give you kind of an intuition here. So here's data. You don't know what to do with it. I mean, you can either divide it to 16 boxes, or you can say, well, I'm going to choose all the vertical things here. I'll get 4 clusters or 4 horizontals. You have no clue. But if I give you a few examples, so I'm coloring some of the data points, now you know what I want, right? So that's the intuition I want to sell here. So sometimes a little bit of annotation could allow you to decide what is the right distance metric here. Should I focus on vertical distances or horizontal distances in this case? And if you have this idea, now you know what to do. So what do I mean? So I'm going to do a supervised clustering or supervised discriminative clustering. I'm going to take the box that I had before with the standard protocol for clustering, and I'm going to embed it within some learning structure. So I'm going to add label data set S. So again, I'm going to start with some unlabeled data and distance metric. I'm going to compare it to the labels that I have, get feedback, and keep on clustering. So every time I'm going to run the clustering cycle, check against my annotated data, and figure out if I want to change the metric or not. So I'm not going to go into the details, but if you go into the slide here, you can see that you can define a clustering error, and the algorithm that will come up will depend a little bit on how you represent your metric. Assume that you represent your metric as a linear function over the features, the same linear function that we started the class with. Think about perceptron or gradient descent. If you choose to do it this way, then the learning algorithm is going to be, again, a gradient descent algorithm, where what you want to do is you want to learn weights. This time, the weights are going to represent the weights for the features in the distance function. Okay? So, again, I realize I'm waving my hands a little bit here, but hopefully the idea is clear. The goal is to learn the metric. You have to choose a representation for the metric. And here I chose a representation of the metric that is linear. If you go back to this example here, think about there are 2 dimensions. What I'm going to do is I'm going to decide that the X has a high weight and the Y has a low weight. That's going to be my distance metric. With a different type of labeling, I will learn that the Y should have a high weight and the X is going to have a low weight, right? Is this intuition clear? So basically, with a little bit of labels and this representation of the distance, I can learn the right distance and then do the clustering correctly. Questions? Okay. So basically, that's what I wanted to say about clustering. Hopefully, there's enough understanding of what's happening here. And I want to spend the next, I don't know, half an hour or something like this on a set of methods that is called dimensionality reductions. Okay. So I started the previous lecture with this nice picture of points in the space, and I asked you how many. I'm going to start with another set of points, but visualize differently. This is really the way you should think about points, because this is how your program sees the points, right? You don't see them on the plane for two reasons. Either because they are not on a plane, and two, because your computer doesn't have ways to visualize it. That's what they get. So so this is really my input space, and I can ask you, what can you say about it? Is it a single cluster, or maybe you want to divide it to multiple clusters? Or I can ask another question. I can ask you, I have a new point, 1, 1, 1, 1. Is it part of this data set or not? Anyone cares to guess? Anyone can visualize this data? How to do it? So I'm going to call this data, I have 4 dimensions, I'm going to call it X, Y, Z, W. And it turns out that this is the data. X plus Z is between 1 and 2. So the answer is yes, 1, 1, 1, 1 is there. And if you want to visualize it, this is how it looks. But it's hard to know. It's hard to know even when what I gave you is just 4-dimensional data. Really, you don't care about the 4 dimensions. You care about 2 of the dimensions. And it's a very simple data set. So in some sense, that's the goal of dimensionality reduction. Now, the goal is not to tell you whether 1, 1, 1, 1 is there, but rather to simplify the data so that you can do something with it. Sometimes what you want to do is visualize it, and more often than that, what you want to do is use it in other algorithms. Could be in clustering, could be in classification, could be in other things. So the reason I say that, even though the first word here I see is visualize, visualization is often a little bit misleading, because if I give you very high dimensional space and you project it into 2 or 3 dimensions, that's what I can visualize at least, it's often hard to know how to choose. And the method that I'm going to talk about today, even they are not ideal. And they never really show you the data. Now, in papers, you'll see many times that people project data to do the 2 dimensions, and what you see is extremely impressive. Ask them how long it took them to figure out the projection. It's not necessarily the case that automatically you can do it. It's often a lot of engineering to get to the right visualization. But anyhow, this is the goal. The goal is to simplify large data sets by projecting it on a smaller number of important dimensions. And there are many, many ways to do it. The key one that I'm going to talk about today is principal component analysis, PCA. And this is also something that you can play with in the problem set. Basically, find dimensions that capture the most variance. I'm going to explain what I mean by this, the most important dimensions of the data. MDS is a version of PCA that is used, this is the method that is most often used for visualization. Really tries to find 2-dimensional points that best preserve interpoint distance so you can visualize. There are other ways of doing this. So one of my favorite is actually random projection, which is a magical method where you have n-dimensional data with large n. It turns out that you can randomly project the data into logarithmic dimension. So if you started with 1,000 dimensional space, choose log 2 of 1,000, typically is 10 or something like this. It's huge, from 1,000 to 10. And the magic of random projection is that it preserves, probabilistically preserves. So with high probability, distances between points is preserved, and also angles are preserved. So this is nice. Typically, it's not going to be 10, it's going to be some constant time log. So there are many methods to do this. And what I want to talk about today is give you some idea of what is dimensionality reduction. As I said, there's a lot of math in all of these, and a lot of this math is in the slides. I'm going to skip most of it. And as I said, try to give intuition. So what is our goal? Or any questions before that? Okay, so as you already know, because you played in this class with a few data sets, many learning problems have high dimensionality. And it's really high. I mean, easily could get to hundreds of thousands or more, just because these are the features that we extract. It could be text, it could be images, either way, or it could be other measurement spaces. In order to be able to learn expressive functions, we need a lot of features. But it's not clear that you need all the features that you dream up at the beginning. And the question is, can you or should you reduce the dimensionality? So this is the problem that dimensionality reduction methods try to address. And the context I'm going to discuss today is really mostly unsupervised learning. Given a collection of data points in an n-dimensional space, find a good representation of the data in an r-dimensional space where r is much smaller than n. You can also think about this in the supervised case, but basically it's the same kind of way. So formally, how do we think about it? So I'm going to think about my data as sitting in a matrix. Columns are my data points. So I have n-dimensional data points, and I have m points. Oh. So each column is a data point here. Okay? So again, think about this. These are really points in 4-dimensional spaces, even though here I show you just their projection to x and z. Just terminology. I can always think about this data matrix, n by m matrix, as a product of r basis vectors. Think about them. Again, I'm talking a little bit of linear algebra, minimal linear algebra. If you forgot all your linear algebra, let it pass. If you remember, you'll get something from these two. Think about it as the natural basis. So n-dimensional vector with one, the ith vector as one in the ith coordinate. So I can always think about this vector as a product of these vectors times the identity matrix, which is what I'm writing here. So x, which is what I had on the left, is a set of m data points. Each column is a data point. And I'm writing it as the product of itself times the unity matrix. I did nothing. I called now this matrix here in the middle, the unity, is the base vectors. Each row here is a base vector, so you can see that these are the unity vectors. And I call these code words for a reason that will be clear. But basically, I did nothing. I'm just writing x as a product of WP. Now, what is dimensionality reduction? What I can do now is I can say, you know what? Instead of m base vectors, I have n vectors, but I'm going to cut the dimensionality. So I'm going to eliminate some of the rows here. Okay? I'm eliminating some of the rows, I have to eliminate the other way around, sorry, I'm eliminating some of the columns here, which means that I have to eliminate some of the rows here. So I'm keeping still the m points that I have, each column is a point, but I'm eliminating some of their coordinates. So instead of n times m, which I have here, I'm going to have only r times m. That's dimensionality reduction, okay? So essentially, I'm using less dimensions for the same point. I'm going to say the same thing about 3 times. At the end, it's going to be clear. So if I started with x equal w times v, when I'm eliminating some of the basis vectors, or if you want, some of the coordinates of each one of the examples on the right, what I'm going to have now is the wv is no longer going to be equal to x. And I can ask, what is the, how well does wv approximate x? What is the distance from the original x to this new product wv? And this will give me an idea of how good an approximation is this dimensionality reduction. And everything about dimensionality reduction has to do with how do I want to measure this error that is called reconstruction error, and what do I want to allow, what kind of transformations or truncation do I want to do for this matrix V? Do I just want to eliminate some of the rows, or do I want to do something more sophisticated rather than just eliminating some of the rows? But either way, I'm going to get here some approximation of x, and I'm going to ask how good is it? Okay, so it's all about data encoding. And my goal is going to be to eliminate, to minimize this distance between x and wv. And as I said, methods differ in what constraints they impose on the data, on this V matrix on the right. And also, this depends on computationally how easy things become. For example, what can I do? I can just say, you know what, this matrix V on the right, I'm going to choose just one coordinate from each column. I had n coordinates, I'm going to choose only one of them. Each vector in the coding matrix V is going to be a single one. All the others are going to be, I'm going to make them 0 or eliminate. This is a dimensionality reduction method. It has a name, it's called vector quantization. And in some application, it's good enough. I could also say, you know what, I'm going to do something to this V, but maintain the fact that the sum of all elements in the vector is 1. It turns out that this method is called PCA, which is the main method people like to use in dimensionality reduction. Although I'm going to now introduce the same method from a different perspective. But this is really what this method is doing. It changes the V matrix by maintaining some of the columns. The sum of the column is 1. Okay, so there are other ways to think about it, and I'm going to try to do this now. So the first thing to think about is the most trivial way to reduce dimensionality. Here is the most trivial way to reduce dimensionality. So I start with an example x that has n dimension, x1 up to xn, and I'm changing it to something that has L dimensions. I'm denoting it here y1 to yl, but you can keep the x's if you want. I basically zeroed out the rest. And the first question you want to ask, okay, you reduce dimensionality. How good are you? How good is this? So we have to decide on how do we measure quality here. And I'm going to decide that we're going to measure it with mean square error, L2, the same thing that we actually started to measure things with in the second lecture of the class when we did gradient descent. So this is a sensible metric. And let's measure. So my L2 distance between this x and y, x my original data, y my truncated reduced dimensionality vector, is x minus y squared. And because I kept the L dimension at the beginning, what I get is that this is the difference, right? The sum from L, or maybe it should have been L plus 1 here, of xi squared. Now, if you think about it this way, think about the data that I have as if it has mean 0. So I already took all the data that I had and kind of shifted it so that it has mean 0. It simplifies life and it doesn't change anything. I just kind of shift to the data. If I think about it this way, and I remember that the variance of a random variable x can be written this way, the expectation of E minus E of x squared, it turns out that this sum of xi squares is really the sum of the variances of the eliminated components. Okay? That's what I got. So basically, and that's what I want to minimize, right? I want to minimize this sum of squares of xi from L to N. So this method, PCA, that also has other names, truncates vectors. It does a little bit more than just truncates, as we'll see, but it generates approximation of the data in such a way that it minimizes the rate of the decrease in the variance. So it tells me which coordinates out of the n I should eliminate so that this gap, as expressed by the sum of variances, is going to be small. Yes?
Is it just plotting the dimension where all the values are not supposed to be?
I don't know yet. So you see what I did here is I just chose the last coordinates, made them 0. And all I showed you here is that those dimensions that I'm eliminating giving the sum of the squares give me the error. And this error can be thought of as variance in the variance of these dimensions. I didn't tell you yet how to choose these dimensions. I just told you, assume you chose these dimensions, that's the error that you will get. Now you can ask, how do I choose these dimensions so that this error is small? Is the right way to do it by choosing those values that are closer to 0? That's a legitimate question, right? The answer is going to be no. And let's look at this example to understand why it's no. So here is data. This data is 2 dimensions. Now again, I plotted it for you, so you see what's in the data. You see that there are 2 clusters. Had I just given you numbers, what would you see? You will see that the x-axis are all these numbers, right? You have no idea what belongs to the bulk on the group on the left and what belongs to the group on the right. You just see numbers, and it seems like there's no gap there. And I could give you the y values, and also you see that you have no idea what's happening here, right? So the red points are really what you see when you get the data. And also, but what would you want to see? What you want to see is a different representation of the data, and the different representation is this. You want me to rotate from x and y, from the red axis, if you want, to this blue axis, and present the data not by projecting the natural way, which it is, which I give you x comma y, which you can think about projecting it on x-axis and on y-axis, but rather you want me to project it on these 1 and 2 axes, what I call here 1 and 2, right? Now that I project it on 1 and 2, just by looking at 1, you know something about the data because you see some gap there. You don't know so much by looking at 2. So what we've learned here is 2 things. One is we learned that the answer to your question is no. Do you agree? Because just by looking at the x coordinate, the minimal x coordinate, or the minimal y coordinate, it gives me nothing. What I first need to do is I need to rotate it correctly. And if I rotate it correctly and the data looks so nice as this one, now I can think about which dimension to eliminate. Which dimension would you eliminate if you can? Here. You'll eliminate 2. It doesn't give you a lot of information. 1 gives you a lot of information about the data. Right? So basically what you want to do is you want to do what I did before, which is this, eliminate some of the coordinates. But before that, you want to project the data on other axes, not on the original axis of the data. So that's PCA. 1, choose axis on which to project the data. 2, eliminate those that have the smallest variance. So now we have to do a little bit of math to explain exactly how we do it. But we want to keep this example in mind because this example shows us that we can eliminate axis 2 because it has low variance. Right? So we just showed before that low variance means low error in our approximation, in our reconstruction of the data. Okay, so the projection on axis 1, this is a summary of what we've done. Projection of axis 1 is maximum variance, and it gives us the clustered nature of the data. And if we so want to represent the data using 1 number rather than 2 numbers, 1 dimension rather than 2 dimensions, I'm going to choose axis 1, or the projection on axis 1, and represent the data this way. Okay, so think about it this way again. So I have data. What I want to do is I want to find a linear combination of the data, which you can think also about as rotation of the data, transformation of the data, so that I can say something about the size of the variance of this y, this linear combination. It turns out that the way to do this, that projection give it to us. So I'm going to say a little bit something about projection. So let's assume that I'm starting with x, my data point, it's an n-dimensional vector. We always think about this as a random vector, so we can talk about variance. As I said, I'm also assuming that the mean of my data is 0. That's easy to achieve and doesn't change anything. I'm taking some column vector, Q. It's going to be a unit column vector. And I'm going to project X on it, which means I'm going to compute X transpose Q. So it turns out that the projection, which I'm going to call A here, so A is a number, is a random variable with mean and variance that are related to the statistics of X. How are they related to the statistic of X? Let's see. So again, if you want to think about it, think about projection to the standard axis, right? What does it mean projecting to the standard axis? Just take the first dimension, or takes the first 2 dimensions. Instead of projection into the first dimension means projection with Q equal 1, 0, 0, 0, 0, 0, 0. This could be a solution, but as the previous example showed, this example showed, not necessarily ideal. I want to choose another Q. But it's the same principle, right? So I'm choosing coordinates. So which Qs do I want? So we can compute the statistics of this projection A, which is the statistics of the projection of X on Q. The mean is 0, just because I chose X mean to be 0. But the variance, if we compute the variance and you believe that I computed it right, what happens is that I compute here the variance of the projection, and this is what I get. I get that it's Q, the vector I'm projecting on, times R, where R is this correlation matrix. This is the data matrix times the data matrix transpose times Q again. So basically the variance of the data depends on my Q, what I project on. Again, think about the example before. When I add this X and Y and I projected on them, I got very bad things. When I chose 1 and 2 and projected on them, I got better variance or understanding of the variance. And this basically is just a quantification of this thing. It basically shows that the variance of the projection is a function of this Q. Q, the vector on which we project. Again, think about this data, and this should be clear. If I projected using the red points versus if I projected using the blue points, I'm getting different variance, right? So I just quantify this. So this function has a name. It's called the variance probe. And our goal is to find transformation, find Qs, such that we can say something about the size of the variance. We want it to be small because we're going to eliminate those dimensions for which the variance is small. We're therefore going to look for this unit vector Q with extreme, actually small values of this probe. So what comes next is a lot of linear algebra, which I'm going to skip, but if you want, you can go to it and read it, and I'm going to summarize. So it turns out that the way to do this is to compute the eigenvectors of this correlation matrix, X transpose, and they will determine for us the Qs that you want to project on. Summary, the eigenvectors of the correlation matrix are pertaining to a zero mean X, define the unit vector Q that represent the principal directions of the data. So this gives me step 1 of PCA, figure out what are the dimensions to project. Once I do this, I call these principal components, and now I have a new representation of the data. This representation is completely non-lossy. It only means that I rotated the data. Now I'm going to drop some of the dimensions, and I'm going to get a dimensionality reduction. So far what I've done is something that, as I said, is completely non-lossy. I started with data, X. I transformed it using the Qs, and I got a new representation of the data, which I call QTX. You can also go back if you want. Once I give you the transformed data, you can go back to X, recover it completely. But because I know that these QX represent the variance, now I can decide which dimensions I'm going to eliminate and how am I going to do it. Again, this is this matrix that I talked about, the QA, and I'm going to take the eigenvalues that correspond to these eigenvectors, sort them, and eliminate all these small eigenvalues. Because they have small variance, I can eliminate the small variance because I showed you before that the sum of the variances is the error that I'm going to make. So I'm eliminating small variances, which means I'm not losing too much. My error is not going to be too bad. So that's PCA. Instead of truncating X in the data space, I'm first transforming it, I'm calling it transforming it into the feature space, and then I'm eliminating the data, eliminating some of the dimensions. Okay, so I want to, so I have a lot more analysis here of the error and what exactly to do. Instead, what I'm going to do is I'm going to give you an algorithm. So this is, again, the example that we saw before. Hopefully now the intuition is clear. What I want to do is I want to eliminate, in this case, x is 2, because I know that this is going to minimize my error. So I'm projecting the vector x on the eigenvectors, and I'm keeping those that correspond to the largest eigenvalues, eliminating those that correspond to the small eigenvalues. Let's see. So I can show you, okay, here's another example that you may help, may not. Here's data. Again, if you want to understand this data, you want to figure out what are the key axes of the data. So the largest eigenvalue is going to correspond to this direction. The second one is going to correspond to this direction. And in general, what you're going to do, of course, here I plot the data in 2 dimensions, but in general, this data is going to be high dimension. What you're going to do is you're going to sort the eigenvalues and choose the principal components that correspond to the largest one, eliminate those that correspond to the smaller one, and you can actually estimate the error because, as I showed before, the projection corresponds directly to the error. And this gives you immediately the PCA algorithm. I'm not going to dwell on it. I mean, this is really what you're going to do, or part of what you can do in the homework. You're going to use these routines. In fact, if you run PCA in sklearn, I think it chooses for you already the largest eigenvectors, the largest eigenvalues and the vectors that correspond to them. So I think you have to do almost nothing. Okay, so I want to finish with give an example here because I think this might illustrate in a better way. This is a famous example that I think I actually even know one of the people that is in this picture that used to work on face recognition. So one claim to fame of PCA was its first application to face recognition, and this was the idea. So you start with a bunch of faces. These are all high-dimensional images, just like what you're playing with in the homework. I think what you have in the homework is 496 or something like this dimensions. So I think it's about what they have here. So I think this, in this case, it was 256 by 256. It's a little bit higher dimension. And what they want to do is they want to figure out what are the key dimensions of the data. 256 squared is too many. So it turns out that not only you can choose the key eigenvectors can be visualized, and they have some meaning. So let's just remember, if we go back to this example of the 2 groups that I show you, each point, let me quickly go there because, so how do you think about this example? Each point here is really a linear combination of x and y, right? That's a representation of a point, a green point. That's how you think about points in their natural space. Each point is a linear combination of 0, 1 and 1, 0, right? Now, when I introduce these, again, each green point is a linear combination of the x-axis, I don't know how to write it, but it has a representation, and the 2-axis, right? So the 1-axis and the 2-axis span all the green points. But they span it in a better way than the x and the y-axis do it. And you could look at the projection on one, and it's meaningful, right? As you can see with the blue points. Exactly the same thing is going to happen here. So what I want to know is, how do I span a face? I want to find the principal component that span a face. And it turns out that if you compute the eigenvectors, you compute the covariance matrix first, just like we talked about before, what you will get is you'll get the best projections for these faces. And here is what you're going to get. So you're going to get a set of eigenfaces, which are the principal components. Each one of them is going to look like a face, right? It's going to be a point in the same space. It's going to be 256 by 256. But they're going to look like this. So these are the 4 top eigenfaces. And every face is a linear combination of these and a few more, right? So if you just take these 4, you get an approximation of the face. So these are the equivalent to the axes 1 and 2, the blue axes that I showed you before, plotted in the phase space. So here is what they did. They took these faces on the right, they generated all the eigenfaces, and I think with this, I don't know, 20 or something, 25 here, they got almost no error. So 25 was enough. In fact, in computer vision, people think about the fact that, or claim that a very small number of eigenvalues retains almost all the information. And there are papers that say that, 7 dimensions retain almost everything across many problems. But basically, that's the idea, right? So once you have this notion of eigenfaces, you can compress the data, you can reduce dimensionality, you can choose how many you want to use, and then you're done. And it turns out that once you work in this space, in this case, I think you take the first 3, you can do classification using this. You basically do nearest neighbor classification, just represent each point, each face, as a 3-dimensional thing, as a function of these 3 images, and you can cluster and classify faces this way, and it works quite well. You can even do more than that. You can think about specific expression, take only the happy faces, and do eigenvectors for them. So these are the top happy faces, or the eigenvector of the happy faces. So with this, I'm going to stop today, take final questions. Okay, so as I said, next time what I want to do is I want to basically remind you what we've done in the class, take questions, and run quickly over everything that we've done this semester. So see you Tuesday. Hi.
When can I start for the internship?
So whenever you want, in fact. So the only issue was just to send you the letter. But whenever you have time, you can start. You can start on Monday if you want. In fact, if you want, so we have a meeting every Friday. You can already come to this meeting if you have time, although this meeting will be a little bit less important for you, so you don't have to come if you don't want to, because
Tomorrow.
tomorrow, yeah. think typically it's at 11. Tomorrow we're starting at 10:30 for Sunday. You can come and people will just know you. If not, come next week. But basically, go to Jen and tell her that, you know, can you start now?
I have some exams. I can start after 4.
Before. But still, if you want to come to the meeting,
Yeah, I will come.
you can come, just you know the people.
10:30, right?
So it's 10:30. I don't know, one of the conferences room in there, you'll see.
Okay.
See you.
So is it, like after this class, is it a good idea to say that for any problem we're dealing with, we should always first do a for component analysis and then
Because, I'll give you an example. Let's assume you want to do OCR, okay, character recognition. So I give you characters and you want to identify A, B, C, D, E, O. So now think about O and Q. Right? O and Q are very similar. Right? There's both of them, if the O and Q is a little bit of a chupstick there, right? So if you do dimensionality reduction, this will disappear. Because who cares about it? Now, and maybe it's true, no one cares about it, unless you want to do this discrimination. So it's not clear that dimensionality reduction, the way I described it here, this is a very good question that I probably should have said. If you remind me, I'll say it next time. You do dimensionality reduction in an unsupervised way, you find the key components of the data. But every discriminative task that you define with this data cares about other things, right? So it may not, it's not a general purpose thing, and you could lose the ability to make some discriminations if you just do it. So you don't want kind of blindly to reduce the dimensionality. So the OQ example I'm giving just to drive this point home. You see, in general, yes, you know, reduce dimensionality, take the kind of little things out. But and it's okay if your goal is just to do, I don't know, to draw things and some, but if your goal is to discriminate characters, don't do it.
okay, I see.
And by the way, another reason for it is that our algorithms today, all the learning algorithms that you've seen in this class, from perceptual to Reno to SVM, they know how to deal with high dimensions very, very well.
Okay.
So if you have the data, deal with the high dimension. Only in cases that you don't have a lot of data, or you are, or other reasons, comprehensibility, visualization, only then reduce dimensionality.
Thanks.
I guess the other question about the seminar. So for example, last week's seminar, can we, I see somebody recording the whole process.
Yes, yes.
Anywhere we can find the resources and the visitors' slides.
Yeah. Oh, the slides I don't know, but all the talks are available. I actually don't know where they are available, but
Is there any?
so you can do, the best thing would be, the person that is responsible is Cheryl.
Sure.
Are you a student here?
Yeah.
So Cheryl is a secretary that sits in the fifth floor.
Lovely.
Yeah, in Levine,
Okay.
yeah. She is, I think, in 502.
502. Okay.
She is responsible. She will be able to quickly give
Oh,
you
yeah.
the pointer to
Yeah,
where
no
you
problem,
can see.
no problem.
If you don't find it after you talk to her, drop me an email. I can find it.
Yeah, definitely. Thank you very much.
Sure. Hi. Yes. So far I don't have a real thing. So you're looking for a research project. So you so I think what I can find is more like a software engineering thing, but not so much a research project, because we are actually busy this summer doing some evaluation, and a lot of my students are going to be working on it. If you So tell me some, maybe you told me already and I forget. So what's your experience, say, with Java?
Previous semester I was in Java. I have some GUI.
So just classes for Java. You haven't actually done any big project or anything. I see. Okay, let me check. So send me another email. What I will do is maybe I will give you something because most of our software is in Java.
I'm willing to learn.
No, definitely it's a good thing to learn, but the issue is that until you know it, I'm not sure that I can give you a real project, but I can definitely give you some starting project.
Yeah.
Okay, but just that you'll know that most of the stuff is in Java, a little bit in Python. We have some interfaces in Python, but I can try to do something with it. So drop me another email just so that I will not forget.
Thank you.
So are you staying here in the summer?
Yeah, I'm going home for 20 days and then coming back.
And you're taking also classes or?
For the summer, no.